For this problem, we're going to have to contend with a couple disjunctions, one on the goal side and one on the given side. And instead of doing disjunctive syllogism a couple times, it can often be a little bit clearer to just take the disjunction on the given side and break it up into a couple cases. So let's try that for this problem. In a situation like ours where our goal is also a disjunction, let's say of the form R or S, then we have to prove R or S in each of these cases separately. But what that amounts to is we really get a choice, right? In each case, we can either prove R or we can prove S, or there's a third option. We could also derive a contradiction somehow. Okay. It's a symbol for a contradiction. We're not going to use that third option in this problem, but it is another valid possibility. Okay, so we're supposed to prove that for any sets A and B, the power set of A union the power set of B is a subset of the power set of A union B. Let's draw a picture and convince ourselves this is true. So we have a couple sets A and B. And if we think about an element, let's say S of the left-hand side here, if it's in the union of these two sets, then either it's in power set of A or power set of B, which means that either S is a subset of A, so something like this, or it's a subset of B, maybe something like this. Okay. And in either case, S is certainly a subset of A union B, and therefore it's an element of the power set of A union B. Now you might wonder whether we could actually make this an equal sign and still have it be true. And in fact, that's not the case. Let's try and illustrate why. If we take a general T in the power set of A union B, then it might look something like this, right? It just has to be a subset of A union B. And that T is neither a subset of A nor a subset of B, so it's not an element to the left side here. Okay, so for some sets A and B, this is not an equality. You can think about what property A and B would have to satisfy in order for this to actually be an equal sign. All right, so let's see how the logic plays out. This is what we're supposed to prove for all A for all B, that this is a subset of that. And we can begin by letting A and B be arbitrary to get rid of those universal quantifiers. And then to prove that subset statement, first we can write its definition, and then we can let S be an arbitrary set to get rid of that quantifier. Now we have to prove a conditional statement, so we can do direct proof, take the antecedent as a given, and got to use some definitions now. S being an element of a union means that it's an element of the first set or the second set. And S being in the power set means that S is a subset of A union B. And then next, S being in these power sets means that it's either a subset of A or a subset of B. And S being a subset of A union B means we use the definition of subset one more time. And then we can let X be arbitrary to get rid of that quantifier. And to prove that conditional, we will once again do direct proof, move that antecedent X in S over as a given. And okay, our goal, X in A union B, definition of union once again, just like we did up here. It gives us that X is in A or X is in B. Okay. And now we have our disjunctions on each side. And so we'll use the one on the given side to get our two cases. That's important. You don't use the disjunction on the goal side to get your cases. You always use it on the given side. Okay, so either S is a subset of A or S is a subset of B. And we bring down the same goal for both cases and bring down our other given in each case. And now let's use the definition of subset one more time in each case. And if we do universal instantiation, we can say that the statement is true for the particular x value that we are dealing with up here. And we know that that x is in S. And so now we look back at our goal, and we don't have, all we have to do to prove that x is in A or x is in B is to prove one of those two things, right? And it looks like in case 1, x in A is the thing that we're going to be able to prove. So let's take that as our goal. And in case 2, it looks like x in B is the thing to do. Okay. And now we're about done, because modus ponens in case 1 gives us x in A, and modus ponens in case 2 gives us x in B. So let's try and write that proof up. First thing was to let A and B be arbitrary sets. And we're going to try and show that statement. So we will say let A and B be arbitrary sets. We show that power set of A union power set of B is a subset of power set of A union B. And then we have another quantifier, so we let S be arbitrary, and this is our new goal. And then to prove that conditional statement, we bring the antecedent over as a given and take the consequent as our goal. Okay. And when we write down that new given, it might be nice to right away sort of say what it amounts to, right? Which, after a couple steps, is that either S is a subset of A or S is a subset of B. Okay, so we'll say let S be not completely arbitrary, but an arbitrary element of the power set of A union the power set of B. And what that means is then either S is a subset of A or S is a subset of B, as we mentioned right here. And then our new goal is right there. So we show that S is in power set of A union B. And it'd be nice to mention what that means right away as well. Just the definition of being in the power set is that you are a subset of, in this case, A union B. So I'll say that is that S is a subset of A union B. Good deal. And then we took the definition of subset here, and in order to drop this quantifier, we let x be arbitrary. In order to prove this conditional, we take x in S as a given, which leaves us with x in A union B as our goal. So I will say let x be not completely arbitrary, but an arbitrary element of S. And we're going to show that x is in A union B. And here's where the cases come into play. So the cases came from this disjunction right here, and the first option was that S is a subset of A. And then, well, the first case brings us down here. The S being a subset of A has that as its definition, and then universal instantiation got us here. And our goal in doing that was to take that together with x and S, which came from over here, and to do modus ponens and arrive at our goal x and A. Okay, so the first case, and we will literally write case 1 just like that, is well, we suppose that S is a subset of A, and then that brought us this conditional, and combining that with x and S, so because x is in S, it follows that x is in A. All right, and then we want to do the same thing for case 2, which came from the second part of our disjunction. Gave us S as a subset of B, and the definition of that gave us this, and universal instantiation gave us that conditional, and together with x and S, modus ponens gets us to x and B. Okay. Okay, so this is going to look parallel to the first case. Suppose S is a subset of B because X is in S. It follows that X is in B. And remember, our goal was that X was in A union B up here. And certainly in either case, what we've arrived at does imply that X is in A union B. Okay, so if you really want to, you could add another line down here, just saying that in either case, therefore, X is in A union B. But I think our reader will realize that we've done that. It's pretty clear. So that means we're done.